Hello and welcome. It seems that we are at the final moments of Nanobiophotonics course. To the best of my ability and knowledge, I have tried to impart everything that I could about this fascinating topic on Nanobiophotonics, and whatever I had to teach, I have already finished. This chapter, chapter number 12, the final chapter, the ultimate chapter, is where it's more or less an opinion, it's more or less a prediction, it's more or less like looking at the future through some sort of a crystal ball, where we try to forecast what's coming, and like any forecast, it will happen that several things may not come true. So, in this particular lecture, the topics, the most important topics of Nanobiophotonics is already covered in chapter 1 to 11. In the final chapter, I decided to give you a direction of the future of the overall Nanobiophotonics field as a whole. Chapter number 11 was also looking at the future high potential, but from a very narrow optogenetics or neurophotonics perspective. Module 12 is the overall general of the entire field of Nanobiophotonics. So, welcome to the final chapter of Nanobiophotonics course, where we discuss research in Nanobiophotonics overview and future directions. And today, I thought that I will bring in a slightly different but very interesting topic, and that is bio-inspired materials for photonics. So, the interesting part here is that thus far we have been utilizing light to reveal biological materials. That is the essence of biophotonics, interaction of light with biological matter. It could be nucleic acid, it could be proteins, it could be a organic assemble like a virus, bigger organs, tissues and cells of various different parts. Here I would like to change it slightly, and here I would like to think or discuss about biologically already existing or inspired by biology, biological materials, organic materials, their interaction with light. Understand the difference. Previously, light was there, this is some kind of a biological matter and interaction, and we are trying to reveal this particular biological matter. Yes. Now, I have a biological matter, I am now subjecting it to different light and trying to scatter light, trying to localize light, trying to diffract light in a specific manner. Both cases, light and matter, light and biological matter are interacting, but here it is slightly reverse. Previously, light was given to image something, brain image, this image, that image. Now, in this particular case, we are trying to look for specific matters, specific biological matters or biologically inspired matters that interact with light and create some sort of a slightly different phenomena, like a different types of interference, different types of refraction pattern. So, basically it agitates the photon in a particular way. So, that is the overall thing, and it's slightly different and it's coming up specifically. So, today's topic, bio-inspired material, is are materials that they draw inspirations from structures and properties found in natural world. These materials mimic the design principle of functions of biological structures, and they take advantage of the unique feature found in plants and create new opportunities for fields like optics, imaging and sensing. So, try to understand this. There is a specific morphology of a nucleic acid such as DNA or RNA. Yes, they are done in a specific wavy like double helical structure. How many double helix do you get in a normal life? Yeah. Similarly, all of you have seen at least the schematic image of a coronavirus, a sphere with spikes, yeah, spike proteins around it. So, these are very unique structures, a DNA or a virus or even the proteins with their secondary and tertiary structures molded along with, and their size is comparable to the wavelength of light. So, yes, light can be made to interact with them and understand them and even modify them, granted, but is the opposite possible, that when they themselves are interacting with light, when these type of smaller structures interacting with light, the reflected light, the transmitted light has a slightly different relationship phase wise, energy wise, frequency wise with respect to what the input is, and thereby this diffracted, this reflected, this refracted light could be utilized for fields such as non-linearity or imaging or sensing, right. So, here instead of trying to reveal these biological matters, we are utilizing these biological matters to modify the light that is falling onto them. The modified light is then being used for some other purposes which may not be biology at all. For example, laser. Can we create laser light? Can we create laser by using DNA as a active material? Yeah, we have discussed DNA, we have also discussed laser. Laser requires an active material where the electron go from lower level to upper level, and then there is spontaneous emission and 2 photons instead of 1 photon get emitted. We have discussed that. So, the active material, can it be some sort of a protein or some sort of a DNA, nucleic acid? Can that be utilized? Can we utilize these kinds of biological matters, nucleic acids, proteins, etc., as some kind of a fluorescent material, specific kind of fluorescent material, which will be like a fluorophore, which we will then tag it, attach it with something else that we want to see. Think about it. So, that is the overall idea, such slightly reversing the concept from light interacting with matter to matter interacting with light. At the end of the day, both are the same. At the end of the day, both are the same, but overall, this is a new way of looking at similar problems. So, that is basically bio-inspired material. So, biomaterials or the materials, biological materials that is specifically pertaining towards photonics application can be roughly divided into 4 different categories. First is bio-derived material, where they are naturally occurring material, nucleic acids, viruses, etc., which you utilize, whose unique properties. There are 10,000 plethora, not 10,000 literally, plethora of viruses, plethora of nucleic acids, several different structures, conformation of proteins. We directly take them, interact them with light and utilize them for a specific application. Then there is bio-inspired materials. Bio-inspired materials are where we try to look into how biological materials are combining together. Say for example, the central dogma, how is this happening, DNA to RNA, RNA to protein. Can we do it for something else? We start with a precursor, a chemical reaction, a biochemical reaction. Can we start with compound A, that after certain time converts it to compound B, and that finally results in creation of compound C, artificially, but inspired by biologically existing materials, biochemical reactions. Third is biotemplates. Here there are self-assembled photonic structures, periodic nanostructure based on a template, based on some kind of a stencil, based on some sort of a map, based on some sort of a existing design. So, you have the virus with spikes around. Can it be used as a template so that the gap, the negative structure can be utilized can be utilized as some kind of a periodic photonic crystal, periodic photonic material. Why not? They have a periodic structure. DNA has a periodic structure, it is a wavy like structure. A virus has those spikes and it has a periodic structure. Can we utilize it like you make sculpture, like you use stencil? You know, sculpture, you have a mold type of thing on top of which you put clay or cement or something like that, and then the mold is taken out and it looks like a statue. Or your stencil where you write A, B, C, D, etc. There is already a mold in which the blank areas where you put the ink and then a particular stencilized A, B, C, D comes. So, can we utilize the existing biological material as a kind of a mold, as a kind of a stencil, as a kind of a template, on top of which something else will be put, and then the virus or the DNA will be taken out, and this mold will have a negative structure, will have the opposite structure, negative or positive is relative, an opposite structure of that, and it might have slightly different biological properties. Finally, bacteria as a bioreactor. We combine couple of bacteria together, their interaction produce some kind of a chemical reaction. The result is some kind of a biochemical compound because of the mating of bacteria, because of the interaction of bacteria, and the final product, the output of bacterial interaction among each other, whatever comes out could be utilized as a thin film. The output of bacterial reproduction or output of bacterial interaction with either a similar types, similar strain or different types of bacteria. So, that is what biomaterials for a photonic application would be looking like, right. So, biological system, why do this? Basically, why do this? So, biological system offers structures that are highly organized, flexible and biodegradable. Obviously, biological materials, so they have to be biodegradable. They are flexible. Imagine how flexible your body is, not just from a gymnastic purpose, but I am talking about the amount of stress and strain it goes through. Its immune system, how flexible it is, the pain management system, how cool or flexible it is. Every single day your sense organs are bombarded by different types of signals, auditory signal, visual signal, touch signals, smell signals, all of that needs to be processed. So, how beautiful and how many variety it has. Can we mimic it? Can we mimic it? An organization. If you ever get a chance to say have a microscope and look underneath something trivial like the wings of a butterfly under the microscope, wings of any insect like dragonfly, the insect dragonfly, anything similar, even mosquito maybe, if you can manage to extract the wings of a mosquito and look it under the microscope, you will see incredible complexity and tremendous amount of organization of different structures, nanostructures or microstructures, variety of them, large number of them, and in a organized way. None of the internal structures present in insects or moths or arthropods or etc. are random. They are organized, they are nano, and there is a variety of them. So, can we mimic that in real life? They can spontaneously form complex structure with hierarchical order, central dogma to cell, cell to tissue, tissue to organ, organ to organ system, and finally, the very complicated organism. These properties make biological system excellent candidates for developing materials that have application in various technologies, including photonics, specifically photonics. So, what are bio-derived materials? Bio-derived materials are derived directly from biological sources. Several of them you already know. The number one being green fluorescent protein. This protein has existed in jellyfish, we have extracted it, we have put it as a DNA template inside different animals, mice specifically, and tried to see in vivo, in life, different areas. You shine light on them, they emit green light. We have bacteria rhodopsin, we have discussed rhodopsin quite a lot, exploited for its photochemical properties like holographic data storage. GFP is used for studying interaction between biomolecules. DNA, as I was saying, it could be utilized as a waveguide as well as laser dyes. It can be utilized for lasers and also thin film waveguides. They can be utilized to guide light from point A to point B with minimum amount of diffraction or any loss, just like you have an optical fiber waveguide. Yeah. Similarly, DNA based waveguide. Think where science is going. And of course, biocolloids, structured biological particles that can form photonic crystal through surface directed assembly. Photonic crystals are the photonic equivalent of semiconductors. Like semiconductors restrict the flow of electrons. In a semiconductor, electrons can only exist in valence band and conduction band. It cannot exist in the forbidden band gap. Photonic crystals are similar, where there are bands of energy like valence band and conduction band. Photonic crystals have bands of energy, allowed band and disallowed band. In allowed band, photons can exist. In disallowed bands, photon cannot exist. Like we have the electronic band gap, the difference between valence band and the conduction band gap. We have the photonic band gap, PBG, between existing lower level energy, lower energy level of photonic crystal versus higher energy level equivalent of conduction band of photonic crystal. In between is the gap where photon cannot exist. Just like you dope in semiconductor to create some extra energy levels inside the band gap and thereby increase the conductivity, photonic band gaps, photonic crystals could also be utilized for exactly similar purposes, where defects can be put, where some extra energy channels could be created in between the photonic band gap, and thereby it could be utilized for various purposes, for example, optoelectronic devices, optical filters, photonic filters, etc., etc. So, we can create those kinds of photonic crystals using biological colloids. Biological colloids, combination of solid and liquid together, and it can be used as a assembly. So, this is exactly what I was talking about. This is the beautiful butterfly wing, and they are not dyes, they are not chemicals. If you look into the wing under a microscope, you will see they have this incredibly organized nanostructure that all reflect a specific amount of light by interference, by diffraction pattern that allows other frequencies to cancel each other, but only one or two frequency to survive, and that frequency happens to be blue or these different shades of blue, thereby the butterfly looks this beautiful. It is not a chemical process, it is a physical process. Under the microscope, the butterfly wing does not look blue, green, white, blue, green, yellow. It looks like this gray ash nanostructure type of thing. It is simply that when sunlight falls into it, all the 7 colors, by interference, only one color survives, rest of the colors are removed. Slight defect here and there changes the color perception, and you have dark blue, light blue, brownish yellow or something like that. So, bioinspired materials are synthetic materials designed by mimicking the process of biological materials. So, if we have this coming from butterfly wing, can we not in lab create an artificial structure such as this? Create an artificial structure such as this, and instead of putting in butterfly wing, we put it in our clothes, in our apparels. At this present moment, the color of your cloth is because it is dyed. Yes, you have put different types of chemicals, you have painted, etc., and after certain 1 year, 2 year of continuous washing and putting it into the sun, it fades, the color fades, color of your clothes fade. But if the structure, if they have a nanostructure, the cotton or the wool have inherent nanostructure like this, then there is something which we call a structural color. Color because of structure, not because of chemical reaction, color because of structure, and this structural colored cloth can stay for a far longer period of time, durable, and they can be anytime customizable, the same cloth slightly by using some sort of a electric current. If you are able to change the nanostructure a little bit, the same blue green color shirt after passing electric current through it, say I am just giving you an analogy, could look like red and yellow. Think how cool that would be. They are actually doing it. This is not science fiction. Look into structural colors in textile. It is bio-inspired. So, these materials often replicate natural hierarchical structure to achieve specific optical functions, and biomimicry, where you mimic, where you copy the biological phenomena, the biological design, is a growing field that focuses on creating multifunctional materials that mimic the complexity of natural structures. Then you have biotemplates. Based on the existing template, as I was telling, so biotemplates are natural microstructure that serve as templates for creating complex photonic material. They can be naturally occurring biomaterials or modified version of them. Viruses are excellent examples of biotemplates. So, this is how the herpes virus organize itself. Based on these structure, this organization, some of you may heard of fractal. Yes, mathematical students or student from physics or electronics engineering might have heard of this thing called fractal. This is how a small design is repeated several times outside and you create a pattern, a self-repeating pattern. So, we can, based on this kind of a pattern structure, this 4 by 4 or 3 by 3, we can create silica nanoparticles of similar nature, and then their interaction of light is then seen to see if they could produce some sort of a photonic crystal effect, metamaterial effect, any kind of interference or diffraction in a specific manner. Right. Of course, bioreactors, as I was saying, bioreactors refer to natural biosynthetic machinery that can be manipulated to produce polymers with specific optical properties. Two bacteria combine, their output turns out to be some sort of their excretion, their output could be considered some sort of a nanomaterial that have a specific optical property. This include bacterial reactor to synthesize customized polymeric structure for photonic application. Pseudomonas putida, this is the bacteria, is one of the source for producing this polymer, polyhydroxyalkanoates. Chemistry people can tell me that this is some kind of a thermopolymer that I have heard, a polymer that is very that's properties changes with heat. So, what are the future aspect? Researchers will continue to draw inspiration from nature to design photonic materials. Biomimicry will play a significant role in creating novel structures. Molecular specificity and hierarchical structure will enable more precise control. DNA based structures will be explored at photonic devices. Biomaterials, biodegradability and eco-friendliness will contribute to the development of suitable photonic solutions. We are basically trying to create the so called biochip. You have integrated circuits, IC, electronics engineers, you know. What if we create an integrated circuits made up of purely biological material? Think about it. They call it the biochip, right. So, in conclusion, biomaterials offers a rich source of inspiration for photonic innovation. The integration of organic and inorganic compounds within biomaterial based platform will yield multifunctional structures, and their eco-friendliness and biodegradability is of course tremendous advantages as compared to purely silicon based or inorganic material based photonic structures, nanostructures. So, these are the concepts covered and these are my references. Thank you very much.